Good morning, everyone. Good afternoon, John. And thank you for joining us today as we begin the INMA Coloquio. My name is Conrado Rillo. I am the director of the Aragon Nanoscience and Materials Institute, a joint research center created in 2020 by the University of Zaragoza and the Spanish National Research Council, CSIC, as a result of the merging of the Aragon Nanoscience Institute and the Aragon Materials Science Institute. The INMA Coloquio initiative aims to bring together top-level international researchers to discuss how their research has an impact on our society, both now and in the future. I wish to thank you all for attending today's colloquia, and in particular, Professor María Jesús Lázaro, our CSIC delegate in Aragon. It is my great pleasure to introduce you John Martinis, who will be the inaugural lecturer of the INMA Coloquio. John Martinis holds the Worcester Chair of Experimental Physics at the University of California, Santa Barbara, and is an expert in superconducting quantum circuits. In 2014, he was hired by Google Quantum Artificial Intelligence Lab to develop the most powerful quantum computer. In 2019, he and his team claimed quantum supremacy, one of the most important milestones of the second quantum revolution. Thanks again to all, and I give the word to Pepa.
Thank you, Conrado. So before getting started, let me thank all the attendees for joining us today. We are very excited about this first seminar. Let me just explain you very briefly a few technical aspects. Those of you that are following us in the YouTube channel might write any question you have for the speaker at any time. Okay, in the YouTube chat, you will find in the right part of the video. Please keep in mind that there is 30-second delay between the video you are seeing in YouTube and the real seminar. Okay, when John finishes, I will read these questions for him. Those of you, on the other hand, that are following us in Zoom are more lucky because you will be able to directly interact with the speaker. For this purpose, I encourage you to use the raise hand button you have, okay, in Zoom. In this way, we will open the microphone on the video, if you like, for you to directly pose your question. You might, if you prefer, however, you can still write your question in the Zoom chat, okay? That's all from the technical part. Let me just thank again John for accepting our invitation. He was really willing to participate and really ready to participate. He made things really easy for us. As Conrado said, he was working in superconducting quantum circuits. He now moved to a different platform, that of silicon, quantum computing. Maybe he tell us a bit about this today. He's one of the most important actors in this development of quantum computing, and I'm sure all of you know him already. Okay. He was so nice also to participate in a very short interview that was published in Heraldo just 2 days ago. I also encourage you to read it. And that's all I wanted to say. So please, John, just start sharing your screen whenever you like. Thank you.
Okay, thank you. Good morning, and thank you for your very kind invitation to talk to you today. And although it'd be nice to be in there in person, what's great is that I can kind of do this easily now. And it's great to be able to share this talk with you. At this point, let me get my talk up here. And here we go. So yeah, today I want to talk about quantum supremacy in a programmable superconducting processor. This was work that was done at Google when I was there and kind of leading the group and wanted to do this experiment as well as, of course, everyone there. Kind of the motivation here is people have been talking about quantum computing for many decades now, and they've been talking about how powerful of quantum mechanics could be in manipulating data, storing data, manipulating it, to the extent that you might be able to run algorithms that are classically impossible. And this idea has been around for many decades, and I think physicists naturally understand that this is possible to do. We kind of understand quantum mechanics. But for software engineers, hardware engineers, let's say Silicon Valley executives, this kind of seemed like a dream that will happen someday in the future. And what we wanted to do with the quantum supremacy experiment is show the power of a quantum computer, demonstrate it as soon as possible, even if it's kind of a crafted and mathematical algorithm, but just show that the basic idea is through a real demonstration of an experiment. And it's been very pleasing that having done this, I think the technical world, not physicists, non-physicists have really seen that, there's something to this and everyone's quite excited. And I think it's good for all of us because there's more funding available to do that. So I want to talk today about, the new design. How do we get this happening? And it's a new design, it's scalable, and it had low 1 and 2 qubit errors. And then basically the quantum supremacy experiment is we run the quantum computer for about 200 seconds. And if you could check it with a classical computer, it would take thousands of years. Okay, and there's clearly a big scale. And the basic idea here is we're doing some kind of computation on this really huge quantum Hilbert space. And that's where you're getting the power, about 10 to the 16 states, basically being manipulated in parallel. But more as important as that is, I also say that the machine works well, and we validated that it worked well with how the error rates. And the good news is we don't see any additional decoherence physics when we build this. So you don't expect that theoretically, but there could practically things can go wrong. You always have to test the theory. And the good news is everything's working okay. We still have a lot of problems to solve, but nothing came up to prevent that. And I'll explain that data. And then, of course, it opens up a powerful era of powerful processors where now, people have to look to make, useful applications, not just powerful. And I'll talk a little bit about that. So I like to talk a general colloquium to talk about why quantum mechanics can process data so well. And the basic idea in quantum mechanics, you can have a superposition of two quantum states, and you can code your system, one quantum state being 0 and one quantum state being 1, and going to be in a superposition of, let's say, 0 and 1. And of course, classically, you have a state can only be 0 or 1, but quantum mechanically, it can be in a superposition, both at the same time. And the basic idea in the quantum algorithms is you can take this state of 0 and 1 and run that one state through an algorithm to basically find the answer to what happens to a 0 and what happens to a 1 simultaneously, done in parallel. And then you get a speed up because you're now processing things in parallel. Now, 1 qubit, it's 2 states, it's nice, but it doesn't necessarily do anything powerful. But what happens, of course, is if you start having more qubits, it's like having more bits. It's more powerful if you have more bits, more powerful to have qubits. If you have 2 qubits, you now have 4 possible states you can be in a superposition of. And if you have 3 qubits, that would be 8 states, and 4, 16, and 5, 32. And you see the amount of states that you can parallel process is going exponentially with the number of qubits, where of course, classically, the power goes as the number of bits. In quantum computing, it goes exponentially. So that's really great. And then by the time you get to something like 50 qubits, 2 to the 50 is a huge number. And then you're challenging what a supercomputer can do. And that's what this talk about. And by the time you get up to something like 300 qubits, and if you can operate them properly, okay, that's hard. But if you can do that, 2 to the 300 is a number that are more states than there are atoms in the universe. And clearly, You could never do that with the classical computer. So that's kind of the long-term vision, to take advantage of that. Now, of course, let me just state for the people who haven't heard about this, in the end, you do this parallel processing, but you have to do a quantum measurement. And quantum measurements gives you, say, 300 bits of output. So you kind of reduce the amount of information that you get when you measure. And since that's so much smaller, that means you can only run certain algorithms to take advantage of this. And people have been working hard. There are important algorithms, but it's not like you can speed up any classical algorithm. Okay, so let's talk about superconducting qubits, which is what we were working on, and I've been doing since the mid-1980s, in fact. And these are just electrical circuits made out of superconductor operating at low temperatures with the size scales of hundreds of microns or maybe a millimeter or so for the qubits. And because they're macroscopic, they're large, they're relatively easy to control. And if you look at this picture on the left, the brown is aluminum metal, the dark brown is an insulator, and these two lines coming in at the right and the bottom are actually the control lines we use to do that. So those are very small, much smaller than our quantum atom, and that makes it kind of easier to bring things in and wire and control it. Being an electrical circuit, it has engineered properties, and we use both quantum mechanics and a lot of microwave engineering concepts to understand what's going on. And then in the end, it's built like a computer chip. So, building one good is hard, and it took a long time, decades to figure that out. But once you know how to build one, then you can step and repeat and build more of them. Still, there's more problems to solve, but in the end, you know how to build it. It's just a question of how to design it and how to make it properly. So those are the good things about the hard part is actually to get the qubits to work well. They're macroscopic, and a lot of things can go wrong with it. And the field over many decades have figured that out. So the way to understand this is a nonlinear electrical oscillator. So what happens is this blue bar here is an island. It forms a capacitance to the ground plane. And down at the bottom here are two crossing of aluminum wires with a very thin oxide in between. And that forms a Josephson tunnel junction where superconducting Cooper pairs can tunnel back and forth. And the effect of those pairs is to make an inductor. So you make an inductor, capacitor, resonator. And it turns out the Josephson junctions have a nonlinear inductance. In fact, that nonlinear inductance can be mapped exactly to a pendulum oscillator. So the basic idea here is you encode the zero state by being in the ground state, kind of semi-classically drawn here. And then the one state has one photon of energy, h bar omega, more or less, and has an excitation in it. And you can draw wave functions of the angles drawn here and here. So it's almost harmonic oscillator-like. It's nonlinear, being a pendulum. That means that the 0, 1, and 1, 2 transitions are at different frequencies, so you can address the quantum transitions as you need to do that. So just show you some data, how it works. We just let the qubit decay to the ground state. We then pulse on microwaves on resonance with the transition frequency, and that creates a 0 to 1 and then 1 to 0 transition. So you're doing a bunch of transitions between 0 and 1. And then we vary the amount of time that's on, and then at some point we measure that and we get a 0 or 1, as you do with a quantum system. And you do that 1,000 times or so to get a probability. So this is a plot of the probability to stay in the ground state versus this microwave pulse time. And initially it's in the 0 state, and then at, it's 20 nanoseconds, you go to the 1 state, and then another 20 nanoseconds, you go back to the 0 state. And it just oscillates back and forth in what's called a Rabi oscillation. Now, what's nice is if you think about this 20 nanosecond pulse, that's a not operation. 20 nanoseconds takes you a 0 to 1 or a 1 to 0, just like classically. But in quantum mechanics, you can do a continuous knot. In fact, if you pulse it, instead of for 20, it's 10, that creates the 0 state to the 0 plus 1 state I talked about earlier. And that can be thought of as a square root of knot, such that a 10 nanosecond square root of knot and a second 10 nanosecond square root of knot gives you a knot. It kind of defines this weird gate operation. Now, classically, you have no idea what the square root of knot operation does, but quantum mechanically has a very definite change in the state. And that very definite change in the state you can then use to build the algorithms. And in fact, that's a very important operation in building quantum algorithms. And you can see you actually have a continuous thing. So think of it as classical logic, but because of the quantum mechanics, it's a much richer operations than you had classically. And that richness is what allows you to build these algorithms that are very, very powerful. Okay, so here's a picture of the chip. We've been working on this many years. We will need to make a 2D array of it to eventually build more powerful processors and do error correction. So this is the Sycamore chip with 54 qubits, 53 working, and the gray X is the qubit. And then in between the qubits in this square grid array, we have things that couple two qubits together. And that's using some adjustable coupler, which I'll talk about in a minute how that works. And you can do single qubit operations, and then with the adjustable couplers, you can do 2 qubit operations between the neighboring qubits. On the right is a photograph of the chip. It's a few centimeters across. The bottom chip is basically the wiring, which takes the wires from the inside and brings them to the outside where we wire bond to the circuit board. I'll show that in a second. And then there's a second chip on top of the first chip that has all the qubits. And then they're connected via many thousands of indium bump bonds that connects up the wires properly and allows you to do everything. So it took a while to figure out how to build this device, especially doing that. But again, we've been working on it for many decades, and we could kind of understand what to do. So here's the fabricated chip. Below that, you can see a packaging. This is just a circuit board that you wire bond to some circuit board, and then you bring it out to an array of microwave connectors. And for this 50 qubit device, it's around 150 wires or so. And then that particular circuit board and mount is put in the very center of this dilution refrigerator. That's about 0.7 meters across. And that's connected to a low temperature. And then we have wire bundles going into these microwave connectors that go through filters up to room temperature. Some of them go to quantum limited microwave amplifiers, and again, go up to the room temperature where you're going to measure it. And the dilution refrigerator gets to about 10 to 20 millikelvin. And you need to get the low temperatures because we're operating these devices at 5 gigahertz. And you need to be at these temperatures so that the quantum energy h bar omega is much greater than the thermal energy KT, so that thermal noise doesn't swamp you. And we like, going to low temperatures. It has its problems. It's not too hard to do. But what's great is we can build circuits that operate around 5 gigahertz or so. And there's lots of technology around, mostly because of cell phones, but microwaves have been around for a long time. So the electronics and the control is something that you can do and scale up. So it's a combination of frequency and temperature. You try to get the sweet spot to get things to work right. And then here's a picture of the cryostat, wires coming out, going to a rack of electronics, and those are custom D to A and microwave devices that give you pulses. So you have about nanosecond timing. You have 14-bit D to A converters, several hundred channels, 200 channels or so to control the experiment. And of course, you have a huge software stack to learn how to do that. In terms of the actual device, they'll get a little bit technical here, but this allowed us to do the experiment, this invention. So we had the qubits as before, and they're nonlinear LC resonators. And there's a wire coming in here that puts magnetic flux in this loop. And that flux changes the inductance. So we have a frequency tunable qubit. And then it's read out through standard Purcell filter readout. And then connecting the two qubits, we have the circuit here drawn green, which is just another qubit that you can change the frequency. But what happens is this is operated at a higher frequency, the qubit. And what happens is you get the qubit driving this off resonance, which then drives the neighboring qubit. And by changing the frequency of this, the amount of net driving through this virtual state, if you like, can vary with frequency. And the closer you get to the other qubit, the higher the drive. This has a negative effective coupling. You put a positive coupler, positive capacitance around that, and then you can, at a certain frequency, you can get zero net coupling. So the basic physics here is a little bit like coupled swings, coupled oscillators. Is very classical-like, so it's not too hard to understand. And we just, like having this, changing the frequency of the virtual state in between, we can do it. So here's the data. So what we do is we take two qubits in the ground state, and we put in this NOT gate, the pi pulse, to put it into one state. And then we take the two qubits and put them on resonance and turn on interaction, let them interact for a time, and then measure them afterwards. And what you see is in this plot at zero coupler bias, we see the population transfer from 0 to 1 to 0 to 1, or qubit 0 to 1. It just swaps back and forth. And this kind of swapping interaction is how you make the two qubit gate. And then what we do is we put current through here and change the frequency and lower it some. And at some point, this swapping goes away and it's just a white line. You just turned off your coupler. And then you can lower the frequency still a little bit more, and then you can get really fast oscillations. So this is nice. This is actually, experimental data. It's taken us decades, really, to get something that looks that well, but you really get the robust, good operation from all that. We build these qubits, and we can do the single qubit and two qubit operations, and then we have to test, well, how well is the thing working? So the first thing we do is we take a single qubit, say this one here, we turn off the couplers, put all the other qubits off resonance, and we see how well that qubit's doing. And basically, we do a sequence of these NOT and square root of NOT operations, and then we get to a final state, and then we check, is the final state what we expected it to be, given the sequence of gates that we put into it. And judging how close we are to that final state, we can then say, what is the error after, let's say, 30, 50 operations or so. And then what you do is you say, okay, if you have an error over hundreds of operations, you divide by the number of operations, and that gives you the error per operation. So you do that with a qubit, you do that with many qubits. Some qubits are better than others. You make a histogram, and what we like to do here is give an integrated histogram that basically tells you how well the qubits are performing. And on average, you can do something like 1,000 operations before the qubit stops working very well. It's actually 1/e time, but it's a rough number here. About 1,000, and some are working a little bit better and some are working a little bit worse, but you still can do quite a lot of operations. You can do the same thing with the two qubits. You have two qubits, turn them on and off, see how these swapping operations are going, and to get a fidelity. And in that case, this is given right here. In isolated, it's about 0.3% error. And you expect a factor of 2 worse because there are 2 qubits instead of 1 qubit. So it's a little bit worse than that, but still not so bad. Okay, these are measuring qubits isolated, which is what you want to do is start it up. But when you actually use a computer, a quantum computer, just like your cell phone or laptop, you have to have all the gates operating at the same time in parallel, because that's how you get the power of the processor. You're not going to do it one at a time. It's just too slow, and you're going to lose coherence. So we start running these. So we turn off all the couplers, and we measure all the qubits at the same time in isolation, and we do the same experiment and measure the errors. And then that in simultaneous, that gives us the black line. So the black line is a little bit shifted to the right from the dotted line, but not by much at all. So it's a little bit worse, a little bit crosstalk, but not a problem. Do the same thing for 2 qubits on all the different pairs, and then that gives us the green line. And now, okay, things are a little bit worse when from 0.36 to 0.62, but still pretty good. And clearly there's some things to fix and work on there. But basically what's great about this is you can use all these things in parallel, running all at the same time, and get good performance. And this is very, very good to get everything working at the same time under 1% error. Of course, we want to make it better, but this will allow us to do the quantum supremacy experiment. Okay, I'm just to let you know, we can make arbitrary gates with the way that we do these swapping operations. So we have a paper on it. I can answer questions if people are interested in that. In order to get this to work, there's a lot of work behind the scenes. And it turns out that the quantum computer is kind of an analog computer, and calibrating it is extremely important. And that's where you spend all your time trying to figure that out. And there's many, many things you have to calibrate it. And this is, for example, a calibration graph that talks about getting the device parameters and tuning up the single qubit gates and readout and 2 qubit gates and whatever. So there's many, many complicated things you have to do on all the qubits. Just to give you a sense of this, these 2 dots here was the PhD thesis of one of my students who now works at Google. And he wrote a couple of papers on it and did that. And the job, once he got that to work, was to then put that into software code so that the software can replace him, as a qubit operator. And of course, the good thing about that is then you get to do more complicated things. So all this can be automated, and there is some manual tune-up always needed right now. But basically, the device can be tuned up and operated pretty well on its own just by calibrating properly. Okay, so now let's talk about the actual algorithm we're going to run for the quantum supremacy. And the interesting thing about the algorithm we're running is that it is the algorithm, any algorithm you would want is based on what we're doing here. So it's really testing the system in a general purpose way, clear test of the system of whether it's worked properly. And on the right, I have the grid of the 53 qubits. And when you see a single circuit, that's a NOT or square root of NOT operation, a single qubit operation. And then when you see a line between 2 circles, that's this ISWAP or swapping operations that I showed you earlier. And what we're doing is, given its nearest neighbor connection, we're alternating between single qubit operations and the 2 qubit operations, where the 2 qubits go to the 4 nearest neighbors. Okay, so this is general purpose. You cycle with all the 1 and 2 qubit gates, simultaneous gates on all the qubits. Here's a diagram in the center of a center qubit, and looking at this versus time, where the center qubit has the square root of NOT operations. Here we have 3 different phases for the square root of NOT. So there's 3 different types. And then you see the square root of ISWAP operation between the neighboring qubits. So those are the 2 qubits. And you cycle around that in time, and that does it. So the nice thing about the quantum supremacy experiment is, given this is how you're going to do an algorithm, it's kind of the simplest algorithm you can imagine. Is you fix this square root of ISWAP gate, and then you choose the NOT gates in these 3 different phases, and you choose them randomly. They're known, but they're chosen random. So given that it's a known but kind of randomly chosen, you can think of this as a kind of a random number generator or a pseudo-random number generator algorithm. Okay, so this is the device. You measure it at the end. Your microwave controls take about 25 nanoseconds for the single qubits, and the 2 qubits can swap in about 12 nanoseconds. It's kind of amazing that 2 qubits are faster than 1 qubit, but that's what you can do with these adjustable couplers, and that's really useful. Okay, so here we go. Okay, so how does this thing work? How does the validation algorithm for quantum supremacy? What happens is when you run this known, random but known circuit, you're generating essentially pseudo-random quantum gates. However, the output states that you're getting, which include all the possible states, 0, 0, 0, 1, 1, 0, 1, 1, all the possible to the n states, they don't have all the same probability. And if you look at these states and measure their probabilities, you're going to see an output that's analogous to laser speckle, which you see on the right-hand drawing here. This is where a laser goes through frosted glass, it spreads out, but in some direction the light is brighter because you've had constructive interference, in some directions the light is dimmer because you had destructive interference. And the same thing happens here, where certain states will have higher probability and certain states will have lower probability. And basically what we do is we sample with this algorithm those states, which of course are the highest probability, and then we check by running a supercomputer whether the states we measured were the highest probability states. And it turns out that basically because this algorithm has no structure in it, it's been proven the only way to solve this properly is to just do a brute force simulation of all the states. And that's what makes quantum supremacy. It's what makes the algorithm tough to solve. You just have to brute force it. Now, to do this check, we do something called cross-entropy fidelity. And that's with the states we measure, those X's. We look up from the classical computer simulation, solving the Schrodinger equation, what's its probability of. And then we take to the n probability of the state we measured minus 1. And what happens is if all the states had equal probability of 1 over 2 to the n, the fidelity is 0. But it turns out when you go through the math, if you have the coherence and you have the qubit speckle, if everything's perfect, you get a fidelity of 1. So what happens is if it's a perfect match, you get a fidelity of 1. If there's any error at all, you get a fidelity 0. If there's a bit flip anywhere or a phase flip anywhere, it's going to be 0. And that means it's kind of a tough experiment because if you do anything wrong with your hardware, you even code your software wrong so that there's a bit flip somewhere, you'll get 0, the experiment doesn't work. And of course, that's good as an experimentalist because it forces you to do the experiment right. So this, you can actually do system validation, learn to control math. There's a lot of things you can do with it. It's kind of interesting idea. Okay, so here's the quantum supremacy data. We have number of qubits here from 12 to 53. We just turn on more and more of the array. And then we're doing 14 cycles. Each cycle is a single qubit and a 2 qubit. So that's, what is it, 4 to 28, 29 operations that we do per qubit. So let's do 12 qubits, 29 operations. That's about 250 total gates. And we do the experiment with the cross-entropy fidelity, and we get a fidelity of about almost 50%, a little bit under 50%. And that means that, you know, a good fraction of the time, there's no errors when we ran the algorithm. And about an equal amount of times, there are 1 or more errors, and the 0 and 1 fidelities average to give us that value, okay? So then we just start adding more and more qubits, calibrated qubits to the system. And then since there's more qubits and more operations, the number of chance of getting error is going to go up and up. And in fact, the fidelity will go down exponentially, and which is what we see. And by the time you get up to 40, it's a few percent. And by you get to 53 qubits, it's about 1% or so. And this is statistically significant number. We take enough data so we know it's not zero. Okay, and this is more or less what you expect that it would go down. Now we can also do something. Oh, and by the way, checking this up to, let's say, 30 qubits or so, you can do that on your laptop. And between 30 and 42 or so, you have to do that with a good workstation with a lot of memory. And then by the time you get up to 53, you're solving it on a Google data center, taking lots and lots of time on a Google data center. But okay, you can do that. And you can classically verify, and that's fine. We would like to mention there's a kind of a simpler thing you can do, is you take this full algorithm where all the qubits are connected, and you cut them in two and turn off the 2 qubit interactions. So now you're solving 2 quantum systems are disconnected in parallel though, and that's an exponentially easier, way easier thing to solve. Basically, that's a laptop problem. And what you see, when you look at that data, we call it a patch circuit that basically follows the red circles. And that's because the number of gates are more or less the same, so that the fidelity should be about the same, but it's just easier to calculate. And you can actually do something in between where you turn off some of the gates, and with some mathematical simplifications, you can solve that readily. And again, it follows the data. Okay, so this shows that everything's working, and now we're going to go to the real quantum supremacy regime, where we're doing 53 qubits, and now we're changing the number of cycles from 12 to 20. In this particular case, there was a mathematical trick here that we discovered actually after we took the data, that you could calculate this much easier, and that's why it only took 5 hours. But if you just change the sequence around a little bit, you can't use that trick anymore, and you have to brute force it. And now it's going to take weeks or years or thousands of years to check it, running the quantum supremacy algorithm. And we can't do that. So the red circles are not there, okay? However, we can run these proxy circuits of the patch and the lighted, and that we can calculate. And those numbers here you expect the red circles to lie on top of these numbers here. And these numbers, this is a 5 sigma error bar. And this is statistically significant and 0. And thus we have strong indication that if we could solve it, we would actually get a proper number and everything would work out okay. So that's the quantum supremacy regime. That's the data, and we show that the machine is working properly, and it's hard to actually check the machine. Now, at this point, I want to talk a little bit about the quantum science results. And there's some really interesting things you can say about quantum mechanics and quantum computing from these results. And the first thing is to note that when I ran the full circuit or the lighted circuit or the patch circuit, we got the same answer, okay? And this is very interesting because the degree of entanglement, degree of computational complexity is very, very different in these 3 circuits. And that means the errors do not depend on the degree of entanglement, computational complexity. And that's really good because that's a basic assumption of quantum computing. And it's nice that somehow the quantum algorithms are not sensitive beyond just the normal errors I was talking about. And then the next thing is there's no new decoherence physics when we did this. If you go back to the last slide, the solid line here is the prediction from our measured single and 2 qubit errors that I talked about at the beginning of the talk. And those are measured in a very simple way. And all that you do is you take the error and you take 1 minus the error, and then you multiply that fidelity by all the different operations. This is just the classical formula that you would use that you learned in high school about statistics to get the net chance that there are no errors. And it's really amazing that this simple classical formula works well to predict this very complicated quantum machine. And of course, this kind of assumption has been behind how error correction and things work. And it's very nice to see that it's working on a very complex circuit with a huge amount of entanglement and everything still working properly. Thirdly, the quantum mechanics works at this huge Hilbert space. It's 2 to the 53 or about 10 to the 16 state space here. It's previously been tested to something like 10 to the 3, and it's really good to see that nothing unusual is going on in that. And the fourth thing in terms of the specialists here, I told you earlier that if you did a bit flip or phase flip, the fidelity will go to 0. And that's been tested computationally, but you can also do that in an experiment. So I think this was like a 14 qubit. We just took one of the bits, single qubit logic gates, and we put a phase change on that. And you see, when you have a phase flip change by a pi, then the fidelity gets 0, as I promised that it did. And then what's interesting, as you continuously change that rotation angle, you then see a continuous change of a fidelity, which goes as a cosine squared theta over 2, which is exactly the kind of thing you would expect, let's say, if you had a single qubit. And it's really nice that this model of digitized errors, which is fundamental to how error correction work, can be tested in the middle of a complex circuit, and kind of shows that this idea works even in complexity. In fact, this is very interesting. There are things you can do here to test what's going on in the middle of the circuit. And if you can ask me a question if you're interested in that. Okay, so we have the quantum supremacy experiment working. The machine works very well. Google eventually wants to put it on the cloud. And of course, you want to do experiments with it. And I just want to briefly talk about a quantum chemistry experiment that was done in the last year and published already, where we looked at simulating quantum chemistry on this. So in doing that, you have to compile your chemistry to the qubits, Hartree-Fock, fermionic operations to describe the electrons. You have to think about your coupling sequence and suite of measurements. But you basically take the orbitals you would have, in this case, an H6, you run a series of swap experiments, a series of different measurements, and then you can get out the parameters to compute the energy of the system. And what's nice here is the various symmetries in this allows you to correct for imperfections and to get in modest circuits of even a fidelity of 99%, even though you're running very complex things. And then you can do variational optimization. So here's just an example of an H12 molecule, which of course doesn't exist, but you can do it computationally. And if you look at the energy of this versus the separation of all the H atoms, there's a dip and then a sharp rise, as you would expect it for H2, but H12 does that too. And the blue dots are coming from the quantum computer, and the black line is what conventional calculations give that. And the errors is quite small from what you expect. So this is double the qubits, electrons, the prior largest chemistry simulation. At H6, you can get chemical accuracy, which is as good as you need. It's a 10-time number of gates. So it really works quite well with this machine. So there's a whole suite of tools available in Google. There's Open Fermion to do the chemistry of qubits. There's Circ, which how to program the machine. And then there's Sycamore, which again, Google hopes to put on the cloud at some point in the future. And people are already using it, special users. And besides this Hartree-Fock, they've done several other algorithms, quantum adiabatic optimization, Fermi-Hubbard, out-of-time order correlator. The thing I want to here, and this is for a smaller chip that we've also made, what I want to point out here is there's hundreds, thousands of gates in all these algorithms. So it's very nice you can actually be running quite complex quantum algorithms right now and getting very sensible results out of it. And I would say this is really nice because when you get to the level of a few thousand gates, you're really testing your algorithms in depth, and you can test what errors will do and the like. So you're really at a level where you can do not just run a quantum computer, but do meaningful tests of your algorithms on a quantum computer. And this is good for the community that that's possible. Before I end, I just want to talk a little bit about the future. First of all, we are doing error correction, and there is an archive paper that came out recently. The Nature Communications paper will come out, I think, next week, looking at some segment of error correction of correlated errors and leakage to the two-state. One I would say, though, of course, in the future, we have to decrease errors beyond what we're doing to about 0.1% is the initial target, at least. The nice thing right now is our T1 of this device was about 16 microseconds or so, or 20 microseconds. Superconducting qubits can do much better than that. So we think it's possible to do that, but of course it's hard is getting good coherence in a very complex circuit. So that looks doable. I'd have to do the hard thing. I've thought a lot about scaling, and I've had an idea when I was at Google how to scale up to thousands and then millions of qubits. I think it's actually possible to do that, although it's a big engineering challenge. I have a little paper here that talks about the fact that one of the big constraints on scaling is the amount of information you need just in the control circuit. So that gives area and volume constraints. And then finally, I have a recent paper talking about cosmic rays can give you correlated errors. But if you design it properly, you should be able to get rid of it. But there has to be some significant research on that to get it to work. So at that, let me just do a quick summary and outlook. Complex quantum, we've been able to achieve quantum supremacy. We know we can you do powerful computation on a quantum computer. But for me as an experimentalist, the really important thing is these complex quantum computers work as expected with these huge Hilbert spaces with this huge computational parallelism. And we're not seeing any new physics. Of course, there's still some physics that's known that we have to improve, but we can kind of think about that as the single and 2 qubit error level and not in the complexity of the full system. We want to next get to useful. Now, to get to useful, we're going to have to invent algorithms, but I highly suspect you have to improve the hardware. And it's just kind of an interesting time now as hardware is improving, people are coming in with algorithms. It may come together at some point in the next few years. It may take longer, who knows? But we're really in an exciting point now where we might be able to do something useful, and people are working hard on that. And again, I think this is really great. We show that the technology works, and we're happy to see that this is supporting continued investment. And my statement is always, this is very hard. We're going to have to see if we can build it, but certainly we've shown enough that motivates that people should be investing and working hard on that. And it's just really exciting to see all the people around the world trying to make this dream a reality. So that's it. I just want to thank the Google team shown here just about the time we were doing the quantum supremacy experiment. And it's only because the concerted work, teamwork of many, many people in the group that made this possible. There's a lot of things that had to happen. And I give them lots of credit for working very hard to make this happen. Okay, so thank you very much.
Thank you, John. Thank you very much. I'm sorry we cannot clap.
Thank you.
Thank you. Very, very interesting talk. Thank you. So we have already a few questions.
Great.
There is one by Paul form. Paul, if you want me to give you to open your microphone.
If you can just talk it, then I can keep my slides up, and that'll be fine.
Okay, so Paul is asking, do you find it coincidental that the best qubits are located in the center of the chip?
Oh, yeah, I haven't thought about for that a while. So let's look at the data. That's great. Yeah, here we go. Let's see. The best qubits are the ones that are darker, and that's kind of spread evenly. And then the best couplers are also spread around. So there's not a really strong correlation in that way. And yeah, I think there's just a coincidence if there is a pattern there. The big thing that you see is that these things called two-level states that are microscopic defects, and if they land in the wrong place where you're operating a qubit, then you can get worse operation. And you tune it up to avoid that as much as possible. But that's probably the biggest problem right now.
I see. Thank you. I'm also giving the word now to Jose Maria de Teresa.
Yeah, it's just a question about in which clean room is the Sycamore microchip fabricated? Thank you.
Yeah, so the Sycamore chip was fabricated at the UC Santa Barbara clean room, which is a university clean room. And that's where we started it. However, like the bump bonding and some special processes were done in the Google clean room just to keep the equipment really pristine. And the plan now is to build their own clean room now that Google is funding the project bigger to build a special purpose facility for doing that. But you could go quite far with the university clean room. But they did have to do a lot of things to keep this clean. And, they worked hard on that aspect of it, which you normally don't think about when you build scientific devices. But this has enough complexity that you really have to do things right there.
Thank you.
Okay, now, Fernando Luis, I think your microphone is already on.
Yeah, thank you, Pepa. Well, thank you for the talk. Was very, very clear, very nice. Well, a very short question concerning the future. So, superconducting circuits or spins? What do you think?
I try not to say what the winners or losers are going to be, because it's such a difficult system engineering project that it's very hard to know what is going to be easier or harder until you build systems. And we could be ahead right now, and tomorrow or next month, someone will publish a paper that's way, way better. So one thing I like about the superconducting qubits is that they're large, and thus you can get wires into it and build the control system in a good way. The spins are it's kind of nice because they're really small and they're really dense, but the control required for these things are hard. But yeah, we'll have to see. I never talk about what people should be down selecting it in any way. And it's interesting to think about spins, because if you can get a super high fidelity, single qubit or 2 qubit fidelity, even though other things may be difficult, that's a real winner. And it's kind of what I like to tell people is, if you can get super high fidelity, that's fantastic. And you should, people should be working on qubits to see if that happens in their system.
Thank you. Yeah, maybe Pepa can just one additional.
Sure.
So actually, I was perhaps you mentioned it at the end that you are also trying to work on on quantum error correction. Have you tried to implement the unit cell? Because I mean, the size of Sycamore should allow for it, the unit cell of a surface code in this processor.
Yeah, the whole design of the Sycamore processor was to make it upward compatible to the surface code. And the Sycamore processor by itself had enough to do an interesting 2D grid. Of course, they've learned a lot of things since then and fixed a bunch of problems. And they are going to make, or are making, a larger, slightly larger processor to do so that you can do, first order and second order correction and really check that properly. So that's in the works, and they're working quite hard at it. And yeah, everything is designed here to be compatible with the surface code. And that's kind of, it's just quantum supremacy is in fact an easier experiment than doing a really good error correction experiment. So this was a good first step.
Thank you. David Serrate had a question, but I think it was the same that Fernando asked about the spin qubits. There are a lot of people working in spin qubits here. So let's move back to Paul, who has another question. Please, Paul, I think your microphone is on.
Yes, it is. Thanks, Pepa. Well, thanks a lot, John, for this really nice and insightful talk. And also, I would like to thank you for being one of the people spearheading all these efforts worldwide, which give us a lot of arguments locally to influence and redirect investment in this direction, so we can add to this effort. So my question here is about the couplers. I'm wondering if the error in the 2-qubit gates is somehow or in a way related to the coherence of the coupler, which is an actual qubit itself.
Yeah, the coupler, it stays in the ground state and it's only virtually occupied. And that seems to work very well. And I think there's been some more testing on that. And I hear that works pretty well. At this point, I think of course, there's some control errors and other things, but the big error that you have to fix right now is just T1. And in some sense, that's really good news because, people know how to make T1 better. I mean, it's harder to make good T1, but, you kind of know how to do that. So, and then I think if you improve T1 and improve the control sum, my feeling was that you could get at or very near that 0.1% that you need to. But, of course, you're going to have to check all the things. As you make things better, you'll find new errors and you'll have to fix it, of course. But the coupler seems to work pretty well.
So you didn't see in the qubit when the coupler is activated that, let's say, noise leaking from the coupler into the qubits?
No, that's not very substantial. That's right. And in some sense, if the quantum supremacy experiment certainly kind of proves that, in the sense that you measure the single and 2 qubit errors, and then it proves, it predicts the fidelity of the full complicated circuit, which says that things aren't going wrong. Now, in terms of the coupler, okay, the coupler errors, which say take the dark green line when you're doing in parallel, that's more than twice as big as the single qubit errors. So clearly, when you're doing 2 qubit errors, there's crosstalk on things going on, and that there's room to improve there. So if you can improve the control, and maybe there's some things going wrong, but you should be able to push that down. But yeah, so let me just restate that. This is probably the best argument of all. The green line being at 0.62 instead of 0.3, it's saying that there's some small things going on with the couplers that you have to improve upon. And I think the group has been working hard on that, obviously. And I hear they've made some improvements on it.
Okay, thank you.
Thank you. Now, please, Ramon, your microphone is on.
Okay, so thank you for the great talk, John. So I wanted to know your opinion about what are the main challenges in terms of scalability for this technology.
Yeah, so let's go to that. Where is that slide? Here's that slide. I have a one-page archive paper on informational constraints on scaling. I had a longer paper and I can't publish it, so I can't go into much detail here. But I do talk about it a little bit. And there are some real constraints on scaling let me just talk about it here. When we run our qubits, there are about more than 100 parameters that you have to measure and set to get the qubits working right. You think there's a few operations, but with all the waveform shaping and getting all the dirt out of there, it's quite complex. So it's in fact quite a complex amount of information to control the system. And we need that complexity in order to tune up and get the qubits working really well. And when you start talking about that kind of thing, that means you need a lot of digital memory to produce the waveforms to do that. And that memory will give you area and volume constraints on any qubit, okay? And those area and volume constraints, let's just say, around a millimeter squared for area or something like that, maybe even more than that. And that's a lot, even for, state-of-the-art CMOS, okay? It's a lot. So it basically points you to want to build big qubits so that you have the room or area or volume to get your control into the qubits, okay? So that's the biggest thing I would say about that. One thing I would say is, yeah, you'd like to have fewer parameters, simplify the control system. We all have to do that. But right now, our gate errors are, fraction of a percent. It's not 0.1% or 0.01%. If our errors were super low, we could engineer trade-off some of those errors to make a simpler control system. But we have no margin. In fact, we have to improve both. We have to improve everything. And that means that we're in a difficult stage right now where, we have to make the qubits better and we have to deal with this kind of area and volume mismatch to the qubit. And that to me seems to be the most fundamental issue. And then you have to decide how to do it. And again, I have some way to do it, and I unfortunately can't talk about that. But yeah, I would think about information constraints. This is pretty serious.
Okay, thank you.
Thank you, Ramon. Now, please, Esteban.
Okay.
Okay, maybe his microphone is not working. He also wrote his question, so I'm gonna read it. Okay, he's asking about the recent results by the Yai Pan group in China with photons. So he's asking about the difference between the Sycamore processor and this additional demonstration of quantum supremacy.
Yeah, first of all, it's great that other people are doing it. I think that's good for the field. And I hear that the optics of this was very challenging and very well done. So that's great. The one big difference is that is not a programmable machine and ours is a programmable machine. And making something programmable actually brings a lot of challenges. And it's, I don't know, it's comparing an abacus with with a personal computer. I don't know. It's a big thing. So I think they have ideas to do that, and I think that'll be great, but it's really, really hard to do that. The second thing I would point out is I was listening in on some theory conversations, and it's not quite clear to the theorists yet whether that's a computationally hard problem. The way that you use squeeze states and then kind of linear optics, they assumed, and a lot of people thought it was hard computationally, but it's not obvious. And there was a lot of discussion. And I think people are just seriously calculating that and trying to understand that now. And you have to give them a few more months to say whether that's a hard computational problem or it's something that they can do. So, I think it's great that they published it. They know that it's hard right now. But, when the quantum supremacy experiment, there was a lot of discussion in the few years before that this was a hard computational problem, and it's been further solidified that way, and they'll have to define that. The other thing I would say is that our experiment naturally leads to error correction and bigger machines. And it's not, we'll have to see, whether that can be, scaled up and made programmable in a useful way. So again, it's great, and we'll see what happens with it.
Very nice, thank you. There is one question by Alejandro González Tudela, who has no microphone, so I will read it also. He says, do you think that having more complex qubit connectivity can lead to improve performance, or will it be detrimental?
Yeah, that's a really good question, because that's a part of the architectural architectural decision you have to make. The nice thing about 4 nearest neighbors is you can run the surface code error correction, which is kind of the lowest threshold, best threshold error correction thing out there right now. So that matches very well. But if you had more connectivity, then obviously better. And for example, in the ion traps, they tout that as great. And of course, it's very nice. Now, when you're running 20 or 30, 50 qubits in the NISQ era, that's actually a big advantage. But when you start building an error-corrected machine, you don't necessarily need that, say, for the surface code. So, and of course, what we want to do long-term is build that error correction, and 4 nearest neighbors is fine for doing that. When you look at your classical computer, every transistor is not connected to every other transistor. So, there's always an architecture issue, and you don't want to fan it out or connect it too much. And basically, the more you connect a qubit to, the easier it is for there to be errors and problems happening and harder to get it to work. And we were just really happy we went from 2 nearest neighbors to 4 nearest neighbors and got that to work with the Sycamore, because that's basically what we need to move forward. But my guess is, the more connectivity you have, the harder it is when you build at scale to get it to work right, and you're going to have to figure out that compromise. But right now, we have something that looks like it should work.
Okay, thank you. Now we have another question by Luis Martin, please.
No, Pepa, there was a mistake from my part. I don't work. Sorry.
Okay, no problem. So, are there more questions from the audience? Let me just give you 1 minute to... Okay, I don't see any more questions in the chat. We have 3 chats. Actually, it's a bit complicated. Sorry if I'm a bit lost. Okay, well, if I may, I also have many questions.
Sure,
One
go
was
ahead.
also about this connectivity. So, as I understood, then you cannot do quantum error connection with connectivity less than 4.
Yes, that's what I understand. And fortunately, 4 in a planar graph works. When I found this out about 10, 12 years ago, and we wrote the surface code paper, I was really enchanted by the fact that something I thought we could build works so well. So this is really magical, the surface code. Of course, people are working on other codes, and that's great. And maybe we can use them, but it's nice to know they're at least an existence proof of something we can build and works well. We just have to get over the large number of qubits. Okay, so yeah, that's not good, but okay.
And then in my second question was in the Sycamore chip, was there also some kind of parasitic next nearest neighbors interaction?
Yeah, there's a little bit, and I think they did some measurement of that, and I forget what those numbers were, but I think it was in the hundreds of kilohertz range, maybe a little bit lower. It was pretty small. And then if you detune the qubits a little bit, which they are naturally, then you can turn it off further. So you try to get rid of those gray things in multiple ways. So you make it small, and then you detune it, and then you can get away with it. The other thing, of course, is the chip has ground planes in it. And as you saw in one of my initial chips, so you have 2 chips with ground planes, and then that helps you minimize your stray coupling.
Okay, thank you.
And those are very important design issues you have to worry about.
Yeah, because I guess from the previous chip to Sycamore chip, you made a big step, no, in the design, mostly in the design of the qubits and the connections between them, right?
Yeah, well, you know, back at UCSB, we made a linear array, and there was, you know, it's fine. It was fine enough for there. And then we made a prior chip to Sycamore that had a different coupling architecture, but it worked again. We've been working on crosstalk for 10 or 15 years. So, you know, basically you use ground planes. Okay, that's but you have to make them really well.
Okay, thank you. So a second chance to pose a question to John Martinez. Is there any other question?
They're nice questions. I'm enjoying this a lot. So
yes, has been already. We had already a few questions.
The questions are the best part for me, because then I get to understand what people are thinking about, and sometimes it even generates really good ideas. So please.
Sure. Okay. Well, if we don't have any other question, we might thank John and all the attendees for joining us, especially you, of course, for being so available and for making this seminar possible, and for being so open to questions, and for the interview and for everything. It was really a real pleasure to have you here. Of course, we would have preferred to have you here physically. Let's hope that in the future this will be possible. Okay. Thank you very much.
Yes, it would be nice at some point to be in person.
I don't know if Conrado wants to say some few words to.
Thank you very much, John, for starting this colloquial series with this wonderful talk. And we hope to be able to have you here presentially soon to illustrate us about the progress of this very exciting field.
Great, thank you very much. Okay.
Okay, thank you very much.
Thank you, bye-bye, my pleasure.
Goodbye, bye.